today right after this class meeting, and my intention for today is to do a high-level kind of review, not all the detail that we did in the video, but just to sort of pull things together subject by subject and then do some problem solving. And especially today, we're going to be looking at those x versus t graphs, bx versus t graphs, and ax versus t graphs for motion in one dimension, which you read about last night, and the relationships to the definitions of displacement, velocity, and acceleration, like the x displacement, velocity, and acceleration. So let's see if this works. I'm going to switch over now to sharing, opening up my PowerPoint file, which again, I am not quite ready with because this took much longer than I thought it was going to, but let me get that open and I will share the screen shortly. I guess I should also just acknowledge that for me, this is a very bizarre situation, having you all behind masks and me behind masks and us all separated here in the classroom. It's even more bizarre with the folks zooming in from home. So it's going to take some getting used to. I'm used to having more dynamic responses with people in the room. Well, first of all, we have many fewer people in the room than are enrolled, but it's hard for me to see your reactions. So make an extra effort to raise your hand or really call me out when you're not so sure what's going on or you have some comment. Still trying to open it up, so be patient. Oh, and I guess I should not forget to take roll here. So there are 6 of us in here, and that agrees with my current knowledge of the role. So we've got Jose in here, I see, and Anna Kate back there. Okay, get something to write with here. Bear with me, everything takes twice as long when we're doing this at a distance. Okay. And Anne Elizabeth Hucker, okay. Natalie Loper, okay. And Jeremy Olius. Did I get that right? Olius. I need to rewrite my phonetic spelling. Put an A-L-L at the beginning. Maybe that will help me. Okay. And Carson, I see you there in the center mass. Okay, and for those of you who are zooming in, just, well, maybe the easiest way for me to do this is to look at Zoom and try to see who I can see. So I see David is there, McGrade. I see Caitlin. Samantha, I see. Anna is here. Tamanji and Andre are here. Okay, and Haley, Katie, and Noah. All right, and as far as I understand, that's everyone. Is there anyone whose name I didn't call out? All right, great. Thanks for your patience with that. Let me now try to start this in slideshow mode. Let me move up to chapter 2 here. Okay, slideshow. Okay. Now let me see if I can share this. It's not doing what I was expecting here. Slideshow setup. So let's go to share screen. I'm just going to share my whole screen with you guys, and then okay. Anna, can you give me a thumbs up if you can see chapter 2 slide? Okay, great. Thank you. So what you read about and watched the videos about last night was about we're restricting our attention to something that's moving in one dimension. Is that there are a lot of cases where things just move along a straight line, but in this case, part of the motivation is it's just simpler to start that way. So we're going to learn some concepts in one dimension, and then later on we'll find that it's not so hard to generalize to one dimension. So our job for today, I think we'll get into this second bullet tomorrow, but for today is to practice with the ideas of displacement, velocity, and acceleration for an object that's moving in one dimension. And by the way, just a little bit of terminology, we use probably, Giancarlo mentions this somewhere in the book. What we're doing now is called kinematics. Kinematics means the way you describe the motion of something without worrying about why it moves that way, just being able to describe, hey, this is how it moved. This is what its position was as a function of time. This is what its velocity was as a function of time. And that's as opposed to what we'll start learning in chapter 4, which is called dynamics. And that means studying the forces that cause motion, and also the exact way that if you know the forces, you'll be able to determine what the subsequent motion is. So we don't really care for right now why something is moving in a certain way. We're just going to take it at face value. Okay, one of the first things I introduced, and I'm not going to, I'm just doing this at a high level, is in order to say where something is as a function of time, you need a coordinate system. And presumably you have all encountered coordinate systems before, especially one-dimensional coordinate systems. So for right now, in chapter 2, I'm saying down here at the bottom, we only need an x-axis, or so we'll say what x, the position, x coordinate of the object is as a function of time. Or maybe sometimes we'll have something moving along the y coordinate, because a lot of times people like to have vertical motion aligned with the y-axis, kind of the way I'm showing right here. So we're not going to have 3 axes or 2 axes, we're just going to have 1 axis. And the assumption is that the object is moving just along a straight line and will line up an axis with it. So we're going to suppose an object in a certain period of time moves, so between time t0 and t1, it moves from position x0 to x1. And we wanted to tease out 2 different notions of how far did it move. And in the videos, you saw a voting question that kind of had this ambiguity in it. If I, for example, standing here, move to the left by 1 meter and then move to the right by a ½ meter, and I ask you how far I moved, there's 2 sensible answers to that question. One is, well, where I ended up was a ½ meter away from where I started. So you might say I moved by a ½ meter, but another person might say, well, you moved 1 meter and then you moved an additional ½ meter. So you moved 1.5 meters overall. That second way of understanding it, where we just add together positively all the distances that are moved through. In other words, how far you walked, irrespective of whether you walked back and forth. That's called the distance traveled. Whereas only taking the distance, the difference between the initial and the final x coordinate. So we're going to call that the x displacement. And I think Giancarlo would just call it the displacement, but I'm putting the x there to get us used to the notation that we're going to see in chapter 3 when we start introducing y and z axes as well, because we're going to see, oh, as I move from position A to position B, I might move along the x direction and the y direction and the z direction. They might all have different displacements there, okay? So the displacement, x displacement, the symbol for it is delta x. And delta x is just the difference between the later x coordinate and the earlier x coordinate. Okay, so the displacement actually can be negative, right? If I later on I was at, later on I was at x1 equals 0, and x0 was x equals 1, then the displacement would be -1. Maybe that's in meters. Whereas the distance traveled is always positive. You're just adding together distances positively, irrespective of what direction you're moving. We're going to use those to give a definition of the average x velocity, which I say later on that nobody really cares about it, or not so much anyway, but it's more of a stepping stone to get to what the velocity is. The x velocity, or the velocity, is supposed to be telling us not only how fast something is going, but what direction it goes. And in this case, the direction is going to be given by the sign of the average x velocity. So the definition hopefully makes sense. It's how far you went in the precise sense of the displacement divided by how long it took, right? Distance over time, etc. This delta x isn't really exactly distance. It might have a negative sign or a positive sign. In other words, if I moved more towards the negative direction in between t0 and t1, delta x would be negative. Whereas if I move more towards the positive direction, delta x would be positive. So there's a sign associated with this that tells you which way you're moving. Whereas the average speed is just the distance traveled in between those two times divided by the times. And I believe there's a voting question in the presentation you looked at home, which shows that sometimes it feels like you're getting cheated by the definition of the average x velocity, in that if I start at this particular position, maybe I'm at x equals 0 right here, I walk over to x equals 1,000 meters, and then I walk back to x equals 0. In between the starting and the ending time of that whole process, my displacement is 0. And my distance traveled would be 2,000 meters, but my displacement is 0. So my average speed would certainly not be 0, because the numerator, it took me a certain amount of time, so the denominator is not 0. But I traveled 2,000 meters, so the numerator is not 0. But if I start and end at the same place, my displacement is 0, and that means I feel like I'm not getting credit for all the work I did. Well, the average x velocity is measuring something different. But again, take some comfort in the fact that we're not really so much interested directly in the average x velocity of an object. Questions on that so far before we go on to the notion of the x velocity without an average in it? So the average x velocity is not telling me anything about what I'm doing at any particular time during that time interval. It's just sort of averaging over the time interval. So at some point in the time interval, I may be moving fast. At other times, I may be at rest. And sometimes I may be moving in the negative direction. It averages all that out. And the important thing is about the average x velocity is you need 2 times over which to average. You're averaging over the period between t0 and t1. There's always some finite time. So to calculate an average x velocity, you need 2 separate times, and you're averaging over the time period between them. Now, here's where things get a little bit complicated, or at least it starts becoming a mouthful. We're going to make a graph of the position of an object on the x-axis, and at least here in the class, it's cut off by my controls, but the x-axis is on the vertical there, and the time axis is on the horizontal. So it kind of looks like, this can be superficially confusing when you're not used to it, it looks like something maybe is moving on a squiggly path in the xy plane, but this is not the xy plane. This is telling me as a function of time what the x-coordinate is. So this represents the motion of something just moving on the x-axis. And so it's telling me at the earliest time that's shown on the graph, it was at some positive x position. As time went on for a while, its x position got bigger and bigger and bigger, and it reached some maximum positive x position at this particular time down there. And as time started increasing even more from there, its x coordinate got smaller from there. It was still positive, but it's getting less and less positive. And then it reached some minimum x coordinate at this particular time down here. And then it started moving in the positive x direction again. So its x coordinate started increasing. So you got to kind of get used to thinking about those graphs. This is not the path of something in the xy plane, but it's rather a somewhat abstract description of what the thing is doing just as it moves on the x-axis back and forth in this case. And taking the definition here of average x velocity, copied from the previous page, it's delta x over delta t. So here we're just imagining, let's take this time and this time. These two times shown on the axis. Let's take that period of time and calculate the average x velocity. Well, delta t is going to be t1 minus t0, so it's just this distance on the time axis, or that amount of time that's elapsed. And delta x is how far it moved. Well, it started out at this x value over here on the x-axis, and it ended up at this x value at that later time, right? So this vertical distance is delta x, and in this case, delta x is positive, right? Because it's moving in the plus x direction. X final is bigger than x initial, so when we subtract them, we get something positive. And delta t is always positive. So when we take the ratio of those two, we get something, you know, if we draw this line in, that's called a secant line that connects the 2 points on the graph at those two times, delta x over delta t is just the rise over the run of the secant line. So we see, if we present the motion this way, that the average x velocity, which is just delta x over delta t, is the slope of the secant line of the x versus t graph. Kind of a mouthful between these two times, t0 to t1. So in this case, it's a positive x velocity, and that just means, you know, it's going in the positive x direction on average between these two times. Similarly, I don't have a picture here, but between this time right here, that's in my initial time, and my later time, my final time there, the secant line would look, you know, almost parallel to the curve there. Or maybe we could take this time right here and a later time over here, and the secant line would connect the 2 points above those times on the graph. And the slope of that secant line would be negative, right? Negative lines are going downward as you move in the plus t direction, and positive slope lines are moving upward as you move in the plus t direction. Zero slope lines, of course, are flat. They're parallel to the t-axis. Now, again, nobody really cares about the secant line because we don't care so much about the average velocity. That's a stepping stone to the idea of the x velocity. And again, Giancarlo, someone, at least one person remarked on the fact that I'm using x's all over the place, and Giancarlo just says the velocity. But this is to get us used to the notation we're going to be using in chapter 3. So this is just a special case, one-dimensional motion of the more general motion we'll see in chapter 3. The x velocity of the object, sometimes people call this the instantaneous x velocity of the object. But, you know, when we say velocity, we always mean instantaneous. So get used to velocity meaning the instantaneous velocity. We don't want to say that polysyllabic word over and over again if we don't have to. The x velocity means how fast and in which direction is the object moving right now, or at this time or later time. We shouldn't have two times when we're talking about the velocity. We only mean right at this time. We don't want to average between two times. We want a single time. And the definition is just, well, we can use the definition of the average velocity. It's right here, delta x over delta t. And we're just told, take it over a very small period of time that includes the time that you're interested in. Calculate delta x over delta t just over a very short period of time. So if you're driving in your car, you're speeding up and you're slowing down, so your velocity is changing all the time. Your speed's changing, maybe your direction isn't. If you want to know what your velocity is right now, you could just say, take a very short period of time, 1/10 of a second. See how far your car moves divided by the amount of time that elapsed, the 1/10 of a second. And that would give you a very, very good approximation of the x velocity at that time. Notice that positive x velocities, well, delta t is always positive, right? Delta t is always t final minus t initial. Time only goes forward. So the sign of delta x is going to be the sign of the velocity x component, or x velocity at that particular time. So if you're moving in the positive x direction, you have a positive x velocity. If you're moving in the negative x direction, you have a negative x velocity. So the sign tells you the direction you're moving. The magnitude of the x tells you how fast you're going. And I think that at least for those of us in the class, I think you who are on Zoom there might be able to see this, but I thought there was a definition of speed that's appearing, but it's covered up by my Zoom controls here. The speed is just how fast you're moving. In other words, if you're moving just in one dimension and the x velocity means how fast you're moving plus the sign tells you in which direction. If you just want to know how fast you're moving, you could take the absolute value of Vx, and that would be the speed. So we denote speed, and I'm hoping you're seeing this on Zoom at home, but maybe I'm on the wrong side. It's hard to tell because part of my screen is covered up by some other stuff. The speed of an object for one-dimensional motion, we're going to have to do something more complicated in 2 and 3 dimensions. We denote just by the symbol V with no subscript. So if it doesn't have that X subscript on it, that just means how fast we're going. And the speed in this case is really simple to calculate. You just throw away any minus signs in the X velocity. Okay. So questions so far? Yeah.
Yeah, in regards to direction for velocity, if it's negative, is it always going to be moving in the left direction? Is that what?
No, I mean, I could have my positive X direction pointed in the direction to the left. So on that slide about coordinate systems, I said, you know, in the real world, there are no axes. I can always orient my X, Y, or Z axes any place I want. I can place the origin wherever I want of that coordinate system. And the same is true for one-dimensional motion. I'm free to take in any picture I draw or in any real situation. If something's moving along one direction, I can take plus X to be either the direction it's moving or the direction opposite it's moving. And so all it means is if your X velocity is negative, you're moving towards the negative X axis direction, right, away from the positive X side. So it's a little bit disconcerting, but that means to us, we always have to be very careful to define our axes at the beginning of every problem, because problems, you know, word problems don't come with axes specified usually. And so that means that you've got to say, I'm going to take plus X to be along the direction this car was moving at time t equals 0, just to be definite. And I'm going to take X equals 0, the origin of the X axis, to be where the car was at time t equals 0. And then you're definite about what your axes mean. That's a good question. Okay, so what we're told is, so here I haven't drawn the picture of this on here yet, but we've got our secant line drawn from there to there. What we're supposed to do then is bring, in other words, I'm going to take my T1 closer and closer and closer to T0 and try to draw the same picture up above. So right now T1 is kind of far away from T0. Let's move it halfway in. When we do that and we draw the secant line, the line that contains the segment that connects those 2 points on the graph, we see it, you know, delta X gets smaller, delta T gets smaller, so the ratio might still be sizable. And I could make it smaller and smaller, and this graphic, which you saw in the video, is supposed to be showing something that you might have seen in a math class before. Certainly those of you who have taken calculus have seen this kind of construction before. That as you take the 2 points that are on the graph and connect them by a secant line and let the second point get closer and closer to the first one, that secant line turns into what we call a tangent line to the curve. And a tangent line means if you're at a particular time, you can draw a tangent line by drawing, you know, bringing your ruler so it just touches the curve at one point. And it's a line that sort of meets up with the curve, goes parallel to it for just, you know, a microsecond there, and then wanders away from it. So it's the line that kind of approximates the curve at that particular time. So there's a tangent line constructed at time t0. And the claim is that the slope of that tangent line, which was gotten from the slopes of the secant line, represents the x velocity of this object at that time. So I can see this at this particular time, t0, the slope of the tangent line is positive, right? It's going upwards as you move to the right, positive t direction. Positive slope means a positive x velocity. And it is, you know, its position is increasing. Its x coordinate is increasing as time goes on. So that makes sense. if we, and there's the thing I was thinking about with the speed, the speed comment we still can't see in the class, but you guys at home probably can see it. Okay, so any questions on that stuff, which you've heard about? I'm trying to do it at double speed relative to what I did in the videos, leaving out a lot of the stuff. But we're going to practice with this graphically. But first, I want to introduce the notion of acceleration, and we're going to look at some of your reading responses.
I have a question.
Yes.
You kind of touched on it earlier, but I couldn't really hear you very well. I'm just like confused and can't like concept how something has a negative velocity. Like how is it moving at a negative? Like is that just back towards where you started at if it's negative or what?
No, it crucially depends on your axes that you've chosen. So let me see if I can figure out, okay, wait, if I stop share, you guys seeing the board
Yes.
now, hopefully? Yeah, okay. So let's suppose something's moving along a one-dimensional region. So it's moving along a line that looks like this. Let's suppose at one earlier time, we'll call that T0. It's at that location, and maybe it does all sorts of crazy stuff, and it's moving back and forth, and at some later time, T1, it's over here. I can't say what the sign of the velocity is. There's no sense to the velocity having a sign until I know what my axis is, right? So if this is the early time and this is the later time, and I take plus x to be to the right, that means that as time went on, it moved more and more in the negative x direction. So in this case, I would say the average x velocity is negative in between these two times because it was moving in the negative x direction relative to what I chose. The opposite would be true if I chose this direction to be plus x. Then it would have been increasing its x coordinate as time went on. It's hard for me to see if you guys can see this, so let me know if I need to adjust the camera or move the board, okay? So that's average velocity. If we say, you know, I'm not talking about average velocity, I'm concerned more with instantaneous velocity, so let's forget about the two times and just say, hey, right now, this object is at this location and it's moving in that direction. If we know that information, if I choose the plus axis to be in this direction, it's a negative x velocity at that instant. If I chose plus x to be on the other side, then it would be a positive x velocity at that instant. So it crucially depends on knowing what your axes are. Okay, good question. Anything else? Just feel free to unmute and if you want to stop me and call out your question if you've got one on Zoom. Okay, let's go back to sharing the screen here. Oops, wrong one. That's not what I wanted. I'm just going to share my whole screen and somehow, oh, here it is. Here's my slideshow. There we go. All right. So here are a couple reading responses. I'm going to have to gather what they are because I can't quite see it in slideshow mode. The author mentioned that when you're talking about velocities and speeds, most people, you know, when we're talking about something happening on the surface of the Earth, that a reference system relative to the Earth is implied. In other words, when we're talking about something moving at 3 meters per second here in the classroom, we always mean 3 meters per second relative to the floor. That's not fundamentally true. You know, if something's moving along at 3 meters per second, but I'm watching it and I'm moving along with it, I'm going to see it at rest. And something might be sitting here at rest in the room, and I'm moving along past it at 3 meters per second, and you in the room are saying it's at rest, whereas I'm moving past it and I say, no, it's moving at 3 meters per second. So we're going to actually talk about this quite a bit more in chapter 4, but the question here was about whether the movement of Earth is negligible or something like that. No, it isn't. We always have to be very careful in specifying things. And for right now, most of the time, our naive assumption is if we talk about something going on in the room, of course, we're talking about if something has a speed or a velocity, it's relative to the floor in the room. To give a velocity, we really need some axes, but we're sort of in the illusion that the Earth isn't moving. The Earth is, of course, moving. It's spinning, and it's going around the sun, and the sun is moving through the cosmos as well. So there's lots of motion, but there's good reasons that we can kind of ignore that, and it's just like we're riding along with the surface of the Earth, and we're just going to pretend the Earth is at rest. But it gets a little bit confusing when you start thinking about the fact that that's not true from other points of view. We will consider that in chapter 4, so hang on to that idea. Second one is there's a difference in the notation between the book and the lectures. Oh, I guess I already mentioned this, but in the book, Giancarlo doesn't use the subscript X. The only reason I do it is on purpose to get us used to the notation that we're going to be using in chapter 3 and beyond for the rest of the course, when we start looking at 2-dimensional and 3-dimensional motion. It also helps you remember that when we're talking about Vx, it doesn't make any sense unless you know what x is. If you haven't defined your x-axis, there's no sense in knowing what the sign of the velocity is. So the x is reminding us that we need to know the x-axis. I'm sure there's plenty more I could have put in there, but I don't want to overdo it. Okay, so here is an exercise that a lot of times is kind of confusing for students, but I was going to, usually I bring in something that's actually executing this motion in the class, but a lot of you are zooming in, so here's a little cartoon of it going up and down. It's a mass hanging on suspended vertically by a spring, and it's going up and down. And we want to plot the position as a function of time. We don't know exactly what it is, but we want something that's roughly right. So here I've given you that the plus x axis is upward. I've chosen plus x going up towards the sky. And I've chosen x equals 0 to be at the location that the bottom end of that heavy mass just barely hits at its lowest point. And just to be definite, we're going to plot x as a function of t for the lowest point on the mass. So at the point where it's at the bottom position, here's a time when it's at the bottom. Oops. Bottom position. Here's another time when it's at the bottom position. It keeps going back to that bottom position. We're going to graph at all the times in between what this motion would look like. And I know you've already seen the discussion of this, but I'm going to switch back to the board here and try to draw this with your help. Hopefully more help from the folks in the room, because it's easier for them to yell stuff out. So let me draw x versus t axes. And let's mark on there. Here's a position where it's at the bottom. I'll just put bot on there. Here's another time when it's at the bottom. Here's a third time. It keeps going back to the bottom. There should be equally spaced if I had drawn it correctly. And now what I want to do is think, well, at time t equals 0, you got to read the problem statement carefully. But the problem statement says, at time t equals 0, it's at its very lowest point, as is suggested by this graph. So at time t equals 0, the point on the graph is x equals 0, because on our axes that I gave you in this particular problem, we chose x equals 0 to be where the bottom of that thing was at this, at the bottom position. The question is, how should I continue this graph as we go forward? Should it go flat? Should it go up immediately, down immediately? How do I think about this? So that is at its lowest position. I'm sorry I'm not showing the graphic, but I'm trying to display the board at the same time here. So it just bounced down to its lowest position, and it's about to start going up. What should the trend in the position be?
Keep going up since the positive x direction is up.
Yeah, it only goes to positive x values here. So the whole graph should be up here in the positive x region, right? The lowest point never gets below x equals 0. So it shouldn't be in the negative x direction. How can we think about at that very lowest point, if we could look at the instant where it momentarily comes to rest at the bottom? It was going down. It's about to start going back up again. At that time, in between going down and going up, what would you say its x velocity is there, given my axes? Positive, negative, or zero? Yeah, it's zero because, well, just a moment earlier it was going down, negative x velocity. A moment later it's going up. What's in between positive, negative, and positive? Well, it's zero. It's got to be zero there. If it's got a zero x velocity, what does that mean about it? I'm going to start drawing a curve. What does it mean about the slope of the tangent line to the curve that I'm about to start drawing? It should be a horizontal line. So that means that if I were to say, hey, it's going up, I'm going to immediately have it go up like that. I know that that's wrong. Well, it's not so wrong. At least I got the initial part right, and it's going up. It certainly is going up, but it's going up in the wrong way. Because look, if I attach a tangent line to there, it would have already at time t equals 0 some positive slope of the tangent line. We said it's at rest, at least momentarily at rest at that time. So the slope of the tangent line should be 0. So that means if I'm drawing a tangent line, maybe in green here, the slope of the tangent line of the curve I'm trying to draw there should have a flat slope of the tangent line. And it's got to eventually go up. And so the only way that that's going to work is to sort of be on the side of a parabola that kind of looks like this. When you're drawing these kind of graphs, you have to be ready to erase, because sometimes you draw things that doesn't quite fit the graph that you're doing. In other words, what we're seeing is the slope of the tangent line at time t equals 0 looks like it's 0. That means it's not moving anywhere. As time steps forward a little bit, the slope of the tangent line becomes a little bit positive. That means it's slightly moving upward. Then it becomes more and more and more positive. That corresponds to it speeding up in the upward direction. It's going faster and faster in plus x. Until at some point here, at some particular time, it looks like it's going as fast as it can go. And that's when it's sort of halfway between the lowest point and the highest point, right? Because it also slows to rest at the highest point. Halfway in between those, it's going, it speeds up and then it slows down on the way to the top. It's got to come to rest at the top. So this is when it's going really fast and upward. There's another point at the highest point where it should be halfway in between the bottoms, where it's at the highest point, and the slope of the tangent line should be 0 there too. So it better come to the top of a hill. Tops of hills have 0 slopes of tangent lines, and that means it's at rest momentarily there, right? And then after that, it starts going down. Going down corresponds to a negative velocity. So that means the slope of the tangent line should start to become slightly negative and more negative and more negative. And then it's going to come to rest again down here. So the slope of the tangent line should become 0 there. There's a lot going on in that graph, and practicing with that is going to take a lot of doing that kind of stuff. So we're going to practice with that more in this class. That's part of what I want to do. Okay, so let's continue on. Of course, during this we would call this one period of the oscillations. This is the second period of the oscillations. Not surprisingly, it does the same kind of thing in that period. So as best as I can quickly sketch it, it might look like that for the motion. Anybody have any problems with what I've drawn here, or questions about why I did things exactly how I did them? It's not an exact graph. I'm just trying to get it qualitatively correct, right? I mean, we didn't really know the exact motion. Now, the challenge here not only is to draw that graph, but in this exercise, to make a graph of Vx versus t. So I'm going to draw some other axes, the x velocity as a function of t, and I'm going to have the t-axis values above and below line up. So here's the time when it's at the bottom right there. Here's another time when it's at the bottom. When it's at the bottom, I don't know that this is necessarily at 0 there, but I'm just marking it on the t-axis. So corresponding points on the t-axis line up there. All right, let's talk about how to start this graph here. Right at t equals 0, should I be starting on the positive Vx axis? We're talking about what it's doing at time t equals 0. Up above, positive Vx, negative Vx, or 0 Vx? It's 0. Several people said here in the class, and that's what we discussed up here. Look, I mean, the argument was it's momentarily at rest. That means 0x velocity, right? The sign doesn't make any difference because you're not going left or right if it's momentarily at rest. So that means the first point on the graph is indeed down here on the t-axis. That means Vx equals 0. Okay, what's the trend? If we just go forward a little bit in time for those first few moments after there, what should this graph be doing? Should it be going upwards, downwards, or staying flat? And why do you say that, Jeremy?
Because the slope's increasing in the distance over time graph.
Sure, we had something that kind of looked like, at least this little piece here, kind of looked like a parabola going up, right? And that means the slope was flat, but it got a little bit positive, more positive, more positive. We're looking at slopes of the tangent line. Slope of the tangent line was 0, little positive, more positive, more positive. That means in that same region of time, the height of this, remember that the value of Vx corresponds to the slope of the tangent line. So if the slope of the tangent line is 0, little positive, more positive, that means the height of this graph at the corresponding time should be 0, little positive, more positive, and so on. So it's sort of going up like that. Again, I don't know this is precisely what it looks like. I'm just trying to give qualitatively the right behavior. Okay, at some point it reached the very highest slope of the tangent line it had, roughly at this particular time here. It reached the very highest value of the slope of the tangent line. And that means the height of this graph that I'm drawing down here should get to a maximum. It shouldn't ever go above that value of Vx, because the slope of the tangent line is the value of Vx. If it's reaching a highest point on a curve, usually that means we've reached the top of a hill. So I'm going to have to kind of round this out there to make it consistent, right? Slope of the tangent line is getting bigger and bigger and bigger. It reaches a maximum positive value. Height of this curve is getting more and more positive, and then it reaches a maximum positive value. After that time, this particular time, it starts to get less and less and less positive, and it goes back to 0. Okay, it was at its maximum value. I'm not sure if my graph is so accurate here, but it should get less and less and less positive and go down to 0. Now I may have to erase that. I'm not sure if it shoots through 0 or maybe it goes a little bit flat there. We'll have to think about it a little bit more. But at least its slope of the tangent line is getting less and less and less positive and ending up at 0. And then slightly negative, a little bit more negative. So slope of the tangent line, 0, a little bit negative, more negative. Value of this graph, 0, slightly negative, slightly more negative. So qualitatively, it just seems like it's zooming through the axis there in terms of how the graph is behaving.
Shouldn't it have a little like horizontal piece there because it's at 0, or is it fine?
I'm not sure what you mean by horizontal. You mean completely flat like this?
Just a little polished, a little flat.
No, no. Because if it were completely flat here, in other words, the question is, should we have a little piece in here where it wiggles flat and then starts heading down? In that little region right there, it would say that the slope of the tangent line over a very small period of time was almost completely constant. But here the slope of the tangent line was positive, less positive, 0, a little bit negative, more negative. So it doesn't seem, at least there's something obvious telling me I should put that little wiggle in there. So I'm going to leave it out. Seems like there's just an instant at which its slope of the tangent line is 0, and that means the height of this graph is here. So always remember, we're putting the x above and the Vx below. Slope of the tangent line tells us the height of this graph. Positive slope of the tangent line means a positive height. Negative slope of the tangent line means a negative height. Okay, continuing on. More and more and more negative. It looks like it's maximally negative somewhere around here. That was when it was zooming downward the most. That might be about here. So that means that the height of this graph should reach a maximum negative value there. That means you're at the bottom of a valley, right? If you're at a maximum negative value.
And then after that maximum negative value, it starts to become less negative, less negative, less negative slope of the tangent line, and it ends up 0 back here. So slope of the tangent line was doing that. That means the value of this graph, the height of it, becomes less negative, and then eventually ends up 0 back there. So it kind of looks like the same squiggly kind of shape here. And I know this is not a calculus-based physics course, but you may have heard, for those of you who have seen some calculus before, that if you have a curve that kind of looks like a cosine or a sine curve, and this looks, you know, at least it's shifted up or down, but it looks like a cosine or a sine curve. When you take the derivative of the cosine, you get a sine-like function. And that's what we're seeing here. This is like a cosine kind of function. This kind of looks like a sine. I'm not being very precise. We don't need to know that relationship here, but at least it seems to bear it out. Of course, during the second cycle, the reasoning would be exactly the same there. So that's how we're going to make those connections between the two. And we're going to practice some more later today after we talk about acceleration. Any questions about that first example? Not necessarily an easy example, but it gets a lot of stuff in there. We're able to practice that reasoning about slopes of tangent lines and the relationship with the graph. Okay. Let me go back to sharing the screen here. And let's now talk about acceleration. And the idea is, we've already done all the hard work. The relationship between displacement, or sorry, position on the x-axis and velocity is exactly the same as the relationship between velocity and acceleration. So what we're going to plot here, and for those of us in class, again, it's a little bit covered by the stuff that you Zoom people can't see. This is actually the same graph, but I've relabeled it. This is not a graph of x versus t. This is a graph of Vx versus t up here. Okay, so it's a totally different graph. It's telling me a graph of the x velocity versus time. And one of the things I'm saying over here to the right is, one thing you can rely on for acceleration is that anytime the x velocity of an object is changing, there's some non-zero x acceleration. And look here, as time goes on, the x velocity is definitely changing. And so we're expecting some non-zero acceleration over that time period. But it is confusing because we're talking about x versus t graphs. Now we're talking about vx versus t graphs, and we have to remember the difference. Okay, but we're going to apply now to this graph exactly the same ideas that we did with velocity. We're going to define the average acceleration. Instead of being the displacement over time, it's going to be the change in vx. Delta always means the final value of that thing minus the initial value, right? So this means Vx at the later time minus Vx at the earlier time. Delta means subtract later minus earlier. Okay, so it's kind of analogous to what we did before. And if you look up at the graph, that just corresponds to the rise over the run for this secant line that I've drawn there. It's a different secant line. The previous one we were talking about was a secant line on the x versus t graph. Here we're talking about a secant line on the Vx versus t graph. So you kind of got to keep stuff straight in your head. It's a little bit confusing. Okay, so the average acceleration is the slope of that secant line by definition, because we made this definition. Nobody cares about the average x acceleration. It's only a stepping stone to the x acceleration, or sometimes, if you really want to be precise, you could say the instantaneous x acceleration. But it means, what is the acceleration of the object right now, or at this particular time, or a later time, or an earlier time? And the same kind of construction as before. Don't be put off by this limit sign. All it's saying is compute this thing over a very small time interval. In other words, if I want to know the x acceleration at this time t0, I should calculate the average x acceleration between that time and a later time and bring that later time closer and closer to the time that I'm interested in. So I'm taking that delta Vx over delta t over a very short time interval. And that's what the x acceleration means. And by the same construction as before, that secant line is going to get closer and closer and closer to a tangent line in going through that process. Okay, so There's a lot going on here, but the slope of the tangent line of the Vx versus t graph at some particular time is the x acceleration at that particular time. And I can calculate it at different times. I guess I removed those from here, but you know, over at this particular time here, if I attached a tangent line to the curve right above that time, it would be going downward. So that would mean at that particular time down here, there's a negative x acceleration. And over at this time where it's shown here, there's a positive x acceleration because of the slope of the tangent line. Okay, there's a lot of confusion associated with acceleration. Most people don't have too hard of a time disentangling what velocity means once you accept the fact that you've got to define what the x-axis is. Strangely enough, positive x acceleration might mean that you're slowing down, or it might not. It all depends on which way you choose your axes. So we've got to think about that as the examples of that. Similarly, strangely, negative x acceleration kind of superficially sounds like you'd be slowing down, but you could be speeding up, or you might be slowing down. Okay, so let's think of some examples where we might be speeding up or slowing down. So here's an example that I went through in the video. Someone at this particular time is walking on the x-axis, so we know which way plus x is. It's going to the right in the figure. The person has a positive x velocity at this instant. How would we describe what this person has to be doing, the kind of behavior, other than moving in the plus x direction? In addition to that, how do they have to be moving to give a positive x acceleration component? And the answer is, well, this case sort of agrees with your intuition. If you have a positive x acceleration in this case, if you're moving in the plus x direction, it just means you're speeding up along the x direction. So this person, if we have a positive ax, that means not only are they moving to the right, but they're speeding up as time goes on. Okay. In terms of the definition, let's go back here to, we're just thinking over a very short period of time. If they weren't speeding up at all, delta Vx would be 0. If we want a positive x acceleration, delta Vx over a short period of time better be positive, right? So that means if they had a certain Vx, maybe 5 meters per second in the plus x direction, and then they go to 5.1 a moment later, the difference between those two would be positive, and my delta Vx would be positive. Okay, similarly, a negative x acceleration, if you're moving in the plus x direction, negative x acceleration means in addition to moving in the plus x direction, you're slowing down at that instant. That means if I was going at 5 meters per second, I'd have to be going at 4.9. So when I do the subtraction for delta Vx, it's 4.9 minus 5, and I get a minus sign in the numerator of delta Vx over delta t. I know that's a mouthful to digest all that stuff. Part of it is just getting used to the terms here. And 0 at ax, what would that look like? You're just standing still in place there? Well, that's one way for it. I'm assuming here that Vx is not 0. So if I were standing still, Vx would be 0. So what would it look like if I'm moving with a positive Vx and I have 0 ax?
Yeah. Vx is constant.
Yeah, Vx is constant. So that would correspond to me, I'm just walking at a constant rate, for those of you on Zoom, in the positive x direction. That would be in between speeding up and slowing down. So what's right in between? Okay, so that maybe agrees with your intuition, but it's all backwards in this second case where, and you know, you won't always be able to choose the axes to make everything agree with your intuition. So in this case, someone has marked out the plus x direction, again to the right, but the person is moving in the negative x direction. So now we know that means they have a negative x velocity at that instant. In addition to moving in the negative x direction, how else would they have to move to have a positive ax?
Change of Vx.
They have to have a negative change in Vx because we're talking about delta Vx over delta t. And that means that, well, maybe I better switch to the board to explain this over here. So we're saying over a very short period of time, the x acceleration can be calculated as the change in Vx divided by the change in time. I'm going to write that as, delta always means final minus initial. So I'm going to write this as Vx final minus Vx initial. Sorry, my V's, they always confuse people. It's supposed to be kind of a script V. Sometimes they end up looking like U's, but it's supposed to be a V with a little tail on it to look like what might be used in the book. So it's an italics V or something like that. Divided by T final minus T initial. Now the denominator is always positive. So the sign of AX is determined by the sign of the numerator. If I want a positive AX, I've got to make the numerator also positive, right? But I'm already told I'm moving in the negative X direction. So maybe in the numerator up here, I'm dividing by a positive number. Who cares about that? But in the numerator, I started out maybe with a X velocity of -5 meters per second. That is going to be, so that's my Vx initial. What should my Vx final be? In other words, should I be going faster in the negative X direction? That would be -5.1, or slower in order to make this thing positive, right? I've got to remember that there's an extra minus sign right here, right? This thing by itself is negative. In this case, there's a minus sign here. And if I want to make this thing in the numerator positive, I can't put a -5.1 there. Right? That would be -5.1 plus 5 would be -0.1. Instead, what I need is something like a -4.9. Sorry, I'm writing sort of small for those of you at home, but that's just how it ended up. So that would mean like +5 minus 4.9 would give me something positive in the numerator. So that means earlier on, I was going in the negative X direction at a certain clip. A moment later, I'm slowing down. So a positive X acceleration can mean I'm slowing down in the negative X direction. Okay, it just sounds superficially confusing. Okay. Similarly, if I have a negative X acceleration and I'm moving in the negative X direction, well, that kind of makes sense. It means I'm speeding up more and more in the negative X direction. And 0 means I'm moving at a constant speed, whichever direction I'm going, right? So it disagrees a little bit superficially with what the words sound like. There's also some discussion in the reading responses about the words deceleration, and it wasn't clear to me. Some people said it seemed to disagree with what was said in the book, and if somebody can point out the page, I'm happy to look it up. I did bring my book with me. Deceleration, there's no doubt, and I bet Giancarlo is clear about this, or at least is intending to say it. Deceleration always means something is slowing down. Your velocity is changing, but you're coming closer and closer to rest, irrespective of whether you're moving in plus X or minus X for your chosen axis. If something is decelerating, it's getting closer and closer to coming to rest. That's what it means. And I think that agrees with our common usage in English. What is confusing is the fact that the word acceleration isn't the opposite of deceleration, even though it sounds like it. Acceleration is just the general phenomenon of your velocity changing. So acceleration might mean deceleration, or it might mean the opposite of deceleration, which is speeding up as time goes on. Okay, so it just generally means not moving with constant velocity. Any more questions about that? There were several reading responses. In fact, maybe I have some reading responses stuck in here. Yes, I do. I got to remember not to put them at the top of the screen because it's hard for us to see when I'm sharing the screen. So when Giancarlo says an object moving to the left is not decelerating, it means it is accelerating, even though it's slowing down. Unfortunately, I can't see all of the text the way this is shown, but maybe if I go out of slideshow mode, yes, there we go. When Giancarlo says an object that is slowing down while moving to the left is not decelerating, already I disagree with that. And I bet Giancarlo isn't saying that because I would have remembered something like that from the text. If something is slowing down, it's automatically decelerating. So if someone can show me where Giancarlo says that, we can certainly look at it. But certainly, the second part of the statement there is correct. If something's slowing down, it's accelerating. Any change in the velocity is an acceleration. Doesn't matter whether it's slowing down or speeding up. We still call that general phenomenon acceleration. But I put this in here because it says something's slowing down, but it's not decelerating. That's definitely not true. Decelerating means getting closer and closer to rest. Okay, now that we're out of the danger zone, let me make this larger and maybe move this over so we can see this. Yes.
I think I know what part they're referencing. I wrote it down. It says deceleration doesn't necessarily mean that the acceleration is negative. So
That's right. Right. So something can be decelerating with a positive acceleration. And what would that mean in terms of the motion? What would we see if I said something is decelerating, but it has a positive acceleration? Well, yeah, we can't say left unless yes, so plus x or minus x. Yeah, it would be moving in the minus x direction, but slowing down. That's definitely decelerating. But if you calculate, we actually did a similar calculation here on the board. If it's slowing down in the negative x direction, then the numerator of that delta x over delta t is actually positive. So we have a positive ax. I know it's confusing. It takes some getting used to. One of the things that I probably mentioned in the video, and I think is good to keep in mind, that you can think of the sign of the acceleration in a few words as being the way the velocity is trending. So that, for example, let's take the intuitive case first, and just so that you can see me walking around. If I'm standing here and I start moving, let's take plus x to be to my left in this case, just for the sake, or sorry, to your left, to my right, I guess. If I start speeding up faster and faster in this direction as time goes on, so I'm going faster and faster in the plus x direction, that would correspond to a positive ax value. And I think most people would say, well, your velocity is trending in the positive x direction. It's getting more and more positive as time goes on. So the trend is toward the positive, right? So trending towards positive means a positive acceleration. So ax would be positive. What if I'm moving in the negative x direction and I say, I want my velocity to trend toward the positive? Well, I'm not even close to the positive, but the only way to get going in the positive x direction is to slow down and come to rest and then start going in the other direction, right? So if I'm going to trend towards the positive, I better be slowing down to get trending in that direction. So slowing down in the negative direction is the same as trending towards positive. It's what you start doing if you want to end up with a positive velocity later on, or more and more positive velocities. Similarly, with negative accelerations, right? If I am moving in the positive x direction and I have a negative x acceleration, that means my velocity is trending toward the negative. Well, I'm moving in positive. How do I get towards a negative velocity? Well, first I got to slow down. So a negative x acceleration means slowing down in the plus x direction. Whereas if I'm moving in the negative x direction and I want to trend to the negative side, that just means going more and more in the negative. So I think it covers all of the cases. So if that helps you, that's just the words I kind of say to myself to help make it not sound so confusing, or so that I don't have to go back to the definition every time and look at the sign of the numerator. In your video, you note that deceleration is always slowing down. Yes, however, the book states that this does not mean that acceleration is negative. So you can be decelerating, but have a positive acceleration if the second velocity of the object is closer to rest. Yes, I believe that if I read that correctly, that's true. you can be slowing down in the negative x direction, and that would correspond to a positive acceleration. It sounds contradictory, but it agrees with the definitions. We've got to get used to testing the definitions and comparing to our intuition. It doesn't always agree with the way we use the words in English. Okay, any other questions about that or reading response stuff that you want to talk about? There are certainly lots of other things that I didn't bring up, and today I was kind of doing this at the last minute, so I grabbed ones that I thought were interesting, but I probably only looked through about half of them so far. I'll try to look through the other ones before tomorrow. There are some voting questions on here, and hopefully you are stopping. It really helps to stop the video, choose one of them, know why you chose it, or at least know that you had no idea before going on to the solution. The point of these is, boy, some of these things are really hard. You know, people don't speak like this in everyday language, and so you really have to think hard to say, if the velocity of a car is non-zero at some time, can the acceleration of the car be zero at that time? What? Nobody ever asks us questions like that in regular life. But yes, in this case, if you think about it the right way, constant non-zero velocity, usually that is one way for the velocity to be non-zero, just have its velocity be constant, and the acceleration is definitely zero if the velocity is not changing. So it sounds superficially confusing, but it's worthwhile to practice with these. And here is a second one. If the acceleration of a car is non-zero, can the velocity be zero? That's sort of flipping the two from the previous question. If the acceleration of a car is non-zero at some time, can the velocity of the car be zero at that time? And the answer again is yes. A lot of times when people see this for the first time, they'll say no. It is somewhat confusing. It's easiest to explain with a graph. So I might say, here's a graph of position versus time. And here's some negative times over here. Here's positive times on this side. At time t equals 0, this object was at rest, right? Because the slope of its tangent line is exactly 0 right there in the middle. So when it reached time t equals 0, it was momentarily at rest. Before then, it had a negative velocity. It was getting closer and closer to 0. And after that, it has a positive velocity. It's getting faster and faster because the slope of the tangent line is getting bigger. What does the velocity versus time look like? Well, I have big negative slope of the tangent line, less negative, 0. That means the height of this graph should be a big negative value, less negative, then 0, then positive, then more positive. Okay, so if you graph that, we can see that, first of all, here is a time when the velocity of the car is exactly 0. Just look at the graph. At that particular time, the height of that velocity is 0. Graph is 0. What about the acceleration? Well, what do I look at in terms of this graph to see whether the acceleration is positive, negative, or 0? The graph that I'm pointing at there. Yeah, you look at the slope of the tangent line at that time. And the slope of it, if you have this looks pretty close to a straight line. If you have a straight line, the tangent line is really on top of the line at every particular time. So the tangent line at time t equals 0 would sort of lie on top of the line there. It would be tangent to the line. And that tangent line has a positive slope. So this is a positive, definitely non-zero acceleration. Slope of the tangent line of the Vx versus t graph is non-zero, and yet Vx is 0. That's what this is asking about up above, even though it sounds really convoluted when you say it in English. It really helps to try to decode those kinds of simple examples like that. A physical example of this would be, for example, I think I said this in the video too. If you take an object, let's call, if I want to match this graph, let's call plus y to be the direction directly downward towards Earth. And let's throw an object up in the air. And I'm going to leave this graph up because I think it will be useful to us. If I throw an object up in the air from my hand, directly upwards, initially it has, and plus y is downward, initially it has a negative velocity, right? Plus y is down, it's going in the upward direction. I tossed it upward. But its y velocity is becoming less and less and less negative as time goes on. It's eventually going to come to 0. That corresponds to the first part of this graph over here, right? Initially, it was moving strongly in the negative x direction. Then the slope of its tangent line got less and less and less. Eventually, it came to rest momentarily. That's when it's at the highest point of its trajectory. Then it starts heading down. And for some reason, I chose plus y to be down here. So it starts having a positive velocity. That means positive slope of the tangent line. More and more positive slope of the tangent line. That means it's speeding up in the downward direction, which is positive for me. So that would be an example of how to make something execute this. And we will talk about fairly shortly that when you throw something up near the surface of the Earth, as long as air resistance is pretty negligible, that the object will move with constant acceleration and sort of behave very similar to this graph. Notice that it looks like from the graph that is shown here, the acceleration is pretty much constant as time goes on for this because the slope of the tangent line is the same everywhere. All right, I'm sympathetic. I know that's a lot of definitions, and we're not going to keep doing definitions at this rate for the whole course. So, you know, if you're feeling like you're going under in terms of all the different graphs and secant lines and tangent lines, that's not the way the whole course is going to be, but we're sort of developing some of the verbal tools that we're going to use as time goes on. This one, maybe it's briefly worth mentioning. A rock is thrown upward. We take plus y to be upward in this case. At the time that it's at its highest point, what's the sign of the acceleration? That corresponds exactly to the example I gave, except that instead of choosing plus y is down, plus y is up. So we found in this other example, that would be a positive acceleration, right? Slope of the tangent line is positive everywhere here. With the opposite axes, this graph would actually go down, and so the acceleration sign would be negative in that case. All right. We're going to stop and do some examples, but I want to go through this relationship that summarizes here what the relationship between the position, velocity, and acceleration graphs are as a function of time. What we've said is that you take, if you draw x on the top, x versus t, then bx versus t, then ax versus t, the slope of the tangent line up here would be positive at this time, right? That should correspond to a positive height here for this graph down below, right? And the slope of the tangent line of this vx versus t graph, at this particular time I'm pointing at, that would be a negative slope, should correspond to the height of this curve down here. That would be a negative height of the graph. We're going to practice with that. Okay, so that's not the next one, but I want to kind of stop there and do some example problems that I don't have written out on a worksheet, so I'm going to draw them out on the board. I'm going to have us start them together and maybe work on them a little bit by yourselves. Any questions on this before we, you know, take a break and do something different? We're going to do some drawing exercise. Okay, good. Let me unshare the screen. Why don't we take a minute, just take a breather, you know. This is a much longer class time than I'm normally used to, and I know it's hard to pay attention, especially for you Zoom folks. I have no love for long Zoom meetings. And if you're just hanging out there, I'm going to draw some position, well, I'm going to draw some graphs on the board, and we're going to try to figure out how to draw, you know, if I draw the position, we're going to try to figure out how to draw the velocity and the acceleration as functions of time to practice that process. And next week, next Tuesday, we'll actually do a lab where we practice with this a little bit more. So if you want to get up and stretch for a minute, that's fine. I'm just going to draw some axes here, hopefully in places that people can see them.
Dr. Kelly, is there a way
Yes.
to move the camera up a little bit? It's hard to
Yes,
see the
you're
y-axis
touching
on
the
the
top.
top. Mm-hmm. Perfect. Almost. Yeah. And
Can you see the top of the axes that I've drawn?
I can see a little bit of it, but we can't quite see the whole board.
I'm trying not to do it too much because I feel like if I,
You don't want to break it. Yeah, that's good. That's good.
well, it's not that I don't want to
can see the
break
whole
it. I'm
board.
afraid I'm going to move it a lot and then I won't be able to get it back.
Okay.
Is that looking good for you?
Yeah, everyone can see the whole board now.
Okay. Can
Thank
you
you.
see where I'm pointing right now?
Yes, if I moved a little screen. There we go. I think.
I just want to make sure everybody can sort of see where I intend to draw. I can always slide this back and forth, so please speak up.
Yeah.
If you can't see something, say, move it to the right, and I'll try to move what I'm doing to the right.
Okay.
So I'm just drawing x versus t, vx versus t, and ax versus t. And the corresponding times are supposed to be the same on the axes that are vertically aligned. We're going to do 3 examples here. Okay, what I'm going to do is start by drawing a graph of x versus t, and we're going to try to decide how to draw what vx versus t. I'm going to have you guys help me do it, and then I'm going to have you try to draw what the ax versus t is if we assume that our vx versus t graph is correct. So my graph, and again, Zoom folks, tell me if you can't see this. The first part of my graph is going to start right at the origin here, and it's going to look like it's on a parabola for a while, and that parabola stops on the way down there. Then there's going to be a flat segment, and then it's going to go to another linear segment that's going down like that. So that's the graph of something that's moving around on the x-axis as a function of time. And it looks like it is first moving in the plus x direction, but then it starts moving in the minus x direction. In other words, its x coordinate gets smaller for a while, and then maybe it sits at rest, and then maybe it starts going in the negative x direction again. My goal here in this first part is to try to construct this graph down here. Now, it's a hand-drawn graph, so there's no exactly right answer. We're going to try to get things qualitatively correct on that graph. And I want to start perhaps with right at t equals 0. That's the first part my graph appears there. We don't have any information before t equals 0. Where does it look like I should start my first point on this graph? Positive, negative, or 0 for vx? And what are you looking at? Is it Carson?
The slope of the tangent line?
Yeah, the slope of the tangent. Now, it doesn't actually go through 0, but it looks like it would continue on like that. Slope of the tangent line looks like it's huge and positive, right? So it seems like the slope of the tangent line on this graph up here corresponds to the height of this curve. The value of vx is equal to the slope of the tangent line. So it seems like we should start way up there because it looks like we have a huge slope of the tangent line. What's the trend as we start moving just a little bit forward in time? How should this graph continue? It's decreasing because I said this is kind of like a parabola. Parabola is going down. This is a downward opening parabola. So slope of the tangent line looks like it's getting less and less and less for that first part. So the height of this seems like it's getting less and less and less. So something like that trend. Okay. The next interesting point on here, important point, is where we're at the top of the hill up here. I'm going to mark that time straight down here. Where do you think we should be on the vx versus t graph at that particular time? At 0, right? Because the slope of the tangent line is horizontal. That's a 0 slope. The value of the slope up there corresponds to the value of the curve down here, or the height of that curve. That's a height of 0. So slope of the tangent line, really big positive, less positive, less positive, less positive to 0. That corresponds to this going down, 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 less positive all the way until you get to 0. Questions so far?
Yeah, can you explain why we started on the top this time again? I was still drawing graphs.
So I was just looking there at what I said, where is the point that's going to be on this graph just at t equals 0? Should I start it up here, down there, or there? And the suggestion was, well, to find the height of this curve, we always look at the slope of the tangent line of this curve. Slope of the tangent line, as we get closer and closer to 0, is positive, and it's getting more and more and more positive, right? These are positive slopes. These are negative slopes, and this is a 0 slope. So we're up in the positive slope of the tangent line region right here at t equals 0. I would attach that tangent line like that. That's a huge and positive slope. So we should give the height of the curve a huge and positive value there.
Okay.
Is that enough on that, Noah?
Yeah.
I have a question too.
Yes.
So how come when we're graphing the velocity, how come we don't start going up and then go down? Because isn't it
What,
speeding up and then
tell me a little bit more
slowing
about
down?
that. Are you imagining we would start here and then go up and then go down?
No, like I understand why we start up higher,
Uh-huh.
but why doesn't it go up at first and then down?
Okay, so let me draw that in green. I don't know how well you guys can see the colors on the video, but the suggestion is, do you agree that it should be 0 here?
Right.
Because the slope of the tangent line is 0. So
Yeah.
it sounds like you're suggesting something more like that.
Yeah.
Initially, it's going up. Can anybody else help me put into words why that would be contradictory? There was a contradiction with the graph up above. Yeah, sure, this is a positive slope of a tangent. I'm trying to attach a tangent line right at t equals 0. It's definitely large and positive. If we're on a piece of a parabola, and I sort of indicated in words that it's like we're on a piece of a parabola here, as you head towards the vertex of the parabola, the slope of the tangent line should be getting more and more and more close to horizontal. So that means it's big, it's a little bit less big, a little bit less big, a little bit less big. That means the height is big, a little bit less big height, a little bit less big height. That means it's going down in height the whole time. Your graph here, or at least the suggestion I made here, would say, look, the height of the velocity got bigger for a moment for that time. And that would mean the slope of the tangent line at some later time should be even bigger. Bigger would look like this. Right? Here it is at t equals 0. It would have to get more steep, but the parabola is actually only getting less steep as time goes on.
Could you draw what it would look like if it got more steep and then less steep for the x-axis one?
Can you repeat that? I didn't hear the very beginning of the question.
Could you draw that instead of just like showing it like how it would look if it was like that? Sorry,
Draw the tangent lines.
No, draw what the x-axis
Let
would
me
look
try
like.
to draw it a little bit bigger so I have more room to draw. Here's a piece of a parabola that we're kind of talking about. The slope of the tangent lines we're talking about are, here's close to t equals 0. So our tangent lines, unfortunately, I don't see any straight edge in here that I can use, but we'll do the best I can. Here's the slope that maybe is tangent to it at t equals 0. A little bit later, the tangent line would look kind of like this.
Mm-hmm.
A little bit later, the tangent line would look, as much as I can draw it just by hand like that. Now, tell me the relationship between the slope of this blue line here that I first drew and the one that's above it.
Yeah, it's less. I
It's
understand
getting
that.
less.
I was just wondering if you could like in these what you drew in the green on for the velocity. Could you show us what that would look like on the x plot? If that makes sense.
On the one that I had before?
Yeah.
Yeah. I'm still not sure I'm getting at what you want me to show, but I can try. So,
Like, I'm just trying to see what it would look like, what the x would look like if it did increase in velocity.
I
and
see
then
what you mean.
decrease.
Yeah, if it agreed with this graph I drew down there,
Yes.
so that would correspond to, I would have to have a slope of a tangent line that started out positive and got bigger for a little bit and then started getting smaller. Let's see if we can do that. As a function of time, slope of the tangent line should start out being positive. So I got to
We
start
can't
moving
really
in the
see you
positive
over
direction
there.
to have a positive slope of the tangent line. But then it has to get bigger. That would correspond to a parabola kind of curving upward. Can you
Dr.
see-
Kelly, we cannot see that portion of
Oh,
the
I'm sorry.
board.
Can we get a
Sorry.
little bit- Can you see here where I'm pointing?
Yes.
Yes.
All right. So if maybe the easiest thing to do would be to just move the camera, but whatever. We need a positive slope of the tangent line. In other words, velocity starts out positive and it gets larger positive. That means the slope of the tangent line starts out with a positive value, but it's got to get more positive. That would correspond to a parabola that's moving up like that. It's opening upward rather than opening downward, which was the example we were doing. I'm trying to draw as best I can a parabola that's curving up like that. Slope of the tangent line is positive. It gets bigger and bigger and bigger positive, and if we wanted to continue on with that example, it reaches some maximum positive value, and then it starts going in that direction. So the slope of the tangent line is positive, bigger, bigger, bigger for a while, and then smaller, smaller, smaller after that. So if I were to draw Vx versus t for the same region of time down here, that would correspond to a positive Vx that gets bigger until about this time, and then starts getting smaller. That was like the example that we were following. Is that enough, Noah?
Yeah, it is, but those two lines look very similar to me, so it's kind of hard to tell, you know, if you were.
Yeah, so the difference is this is definitely not a part of a parabola. Sorry, yeah, this one here.
Okay.
Definitely not part of a parabola, because a parabola never sort of snakes through a region. It's always curving in the same direction.
Okay.
It either opens totally downward or totally upward. This looked like it was sort of opening upward for a while, and then it turned into something that was opening downward, and parabolas don't do that.
Okay.
And I'm just sticking to the statement I made that, well, let's pretend this first part is a piece of a parabola,
Gotcha.
just to be definite. Okay. Let's see, this is about where you guys can see. So we've done part of this. I think what I'm going to let you do is now try to continue that process and do the rest of the graph. So take just 30 seconds or a minute, see if you can continue the rest of the graph for the rest of what we're showing here. In this case, the graph that you're drawing might have some discontinuities in it. In other words, the line might have some breaks in it. So be prepared for that in this particular example. That's okay. Okay, you probably had enough time to either complete this graph or realize that you don't know what to do. So as we continue onward, all of a sudden something drastic doesn't happen there. It happens really at this point over here. So it stays on the parabola until we reach this time where the second dashed line is. And the trend continuing is it was at a slope of a tangent line of 0, then slightly negative, then more negative, then more negative until we reach this time. So The height was 0, then slightly negative, more negative, until we reach that time. It's hard to tell if it should be exactly a straight line, but that's the general trend. It was positive and it went through 0, and now it's down in the negative region, okay? After that, something drastic happens. It jumps onto this other part of the curve, which is completely flat. Slope of the tangent line of a flat curve is always 0. So slope of the tangent line is 0 all the way across there until we get to this time down here. And that means the height of this curve should suddenly jump down to a value of 0. It's kind of hard to see because it's on the axis there, but it should have a height of 0 because the slope of the tangent line above is 0 everywhere. And then again, another drastic transition. It looks like we're on a linear segment here, so the slope of the tangent line is constant and negative all the way until this time where the graph ends. So I go down to some negative value, and it's hard, you know, I guess one way I could gauge it is to say, well, it looked like it was a little bit more negative here. So it shouldn't quite get down to this height. Maybe it's ever so slightly less negative. And it stays, you know, the value of the slope of the tangent line stays constant. So the height of this curve here stays constant and negative. So that's what the graph of the velocity x component as a function of time is going to do. And I should say, you know, this is really confusing for a lot of people the first time they do it. There almost for sure will be an exam question on the first exam that has you practice this kind of stuff. So we want to get to the point where we're going to practice it today. We're going to practice it in lab next Tuesday. There's not so much in the homework that's assigned. I just couldn't find them in the homework collections, but we will practice quite a bit today. We're going to do 2 more right here. Okay, let's continue on. Maybe I made some mistakes in this graph, but let's take this one now at face value to be true, and let's turn it into an acceleration versus time graph. And the idea is what you did to go from here to here, if you follow the definitions through, you do the same thing to this graph to get this graph. Slope of the tangent line here is the height down here to go from velocity to acceleration. So again, let me ask the question, where should I start at t equals 0? Where should I start this graph? Positive, negative, or 0? Negative, because the slope of the tangent line looks like it's already negative there. And in fact, it seems to stay constant and negative all the way, you know, if I take this graph at face value, until I reach this time right here. Constant and negative slope of the tangent line means a constant and negative height down here. Move this over closer to the center, so make sure everybody's seeing it. Okay, then slope of the tangent line up here, well, the height of the graph is 0, but the slope of the tangent line is the important thing, and it's 0, 0, 0, 0 all the way across there. That means the height of this graph is 0 all the way across there. Similarly, in this region, slope of the tangent line is 0 all the way across, so it stays at 0. Now, you might say there's something funny going on here, because to get from there to there, if this is a real object moving, it can't instantaneously change its velocity. So, you know, if I were coming in with a microscope and I said, oh, I looked at this curve really carefully, and it goes down really steeply there for just a tiny little bit of time, if you look closely, then that would correspond to a really negative slope of the tangent line. So maybe for a very, if you go in with a microscope here, this thing jumps down to a really negative value and then jumps back up over a very short period of time. But we're kind of ignoring that for right now. We're just going to ignore the discontinuities and how an actual object could undergo that. Any more questions on that graph before we do another? Okay, I'm going to bump up the complexity a little bit, and instead of giving you x versus t, in this case, I'm going to give you a vx versus t curve. And the vx versus t looks like this. This is supposed to be flat right here. I didn't do the best job of it. Completely horizontal in that past region. Now, of course, this is the same old going down. We could do that. We'll do that later. Let's do the more difficult question, which we haven't really practiced with yet. If I have this graph here, how do I turn it into what this graph up here, the x versus t must have had to look like for that one to be consistent, at least qualitatively? This is a more difficult question, or at least it requires a little bit of new thinking here. So I'm going to ask the same question I did before. Should I start at positive, negative, or 0 height for the x versus t?
Negative.
And why do you say negative? Was it Carson who said that? Somebody on.
No, that was me. Is it just because the area under the curve?
Yes, so the area under the curve, if you followed along with the video, or I think there was a discussion of it in Giancoli, said the area under a curve, and here, for the first part, that area is negative. That tells us about the change in the height of this curve up here. But that doesn't, the change in height of this curve, you suppose the change, so here I could say, following along with that, and I didn't talk about it here in class, but you saw it on the videos. In between this time and this time, we would call this area under the curve negative because it's down below the t-axis. And what that tells me is that, if you followed along with that discussion, that tells me that the change in height of this curve in between this time and this time should be negative. That's not the same as knowing where to start, because notice, for this change to be negative, it could have started up here and went down to there, or it could have started here and went down to there, or it could have started here and went down to there. So you're right, Andre, about this being the connection between the sign of the area and whether you're going up and down or down as time goes on. That doesn't necessarily tell me where to start. So let's think in reverse. This is a little bit of a tricky thing to reason about. By the fact that I know that the value of Vx is 0 at time t equals 0, what does that tell me about the graph up above? It tells me it starts at 0. So is that what the relationship is? If the value is 0 up here, the value is 0 down there? Is that what we said we were talking about? Right. Slope of tangent, at least when I draw them in this order, slope of tangent line above corresponds to the height down below. So if the height is 0 down below, slope of the tangent line is 0 down below. Now there's a lot of ways to start a graph that start with the slope of tangent line of 0. It might have been up here. And maybe it starts, going like that, or maybe it starts going like that. But at least for the very first bit, it better come out going horizontal. So maybe it's up high. But it could have done that down here at 0. And it could have done it down here at a negative value, right? There's just no way to tell. And in fact, all 3 of those are correct answers. Think of it this way. Suppose I say, here I am, I'm at rest, and I'm about to start moving in the negative x direction, right? My velocity is 0, x velocity is 0, and it starts to become more and more negative. So that means I'm at rest, and I'm about to start moving in the negative x direction. Do you have any way of knowing from that description whether I'm near the origin, or I'm near x equals 1,000 meters, or x equals a minus 1,000 meters? No, I could execute starting at rest and then start moving in the negative x direction in any of those locations. So unfortunately, here there's a little bit of an ambiguity. And that's because I don't really know where to start. And again, this is not part of this course, but if you've taken calculus before, you may know something about going from here down to here. Slopes of tangent lines corresponds to taking the derivative of that function. The opposite of doing derivatives is integration. And when you integrate, there's always that annoying plus c that you get. And that means the c isn't well determined. That plus c is going to move the starting point of this curve up or down. But for us, the important thing to realize is that all 3 of those could be correct, and we can choose it for our convenience. Now, I'm going to choose it in sort of an intelligent way. I'm going to look, over the time that we got to draw here, the velocity was negative for a little period of time, but it was very positive for a long period of time. Very positive means this curve is going to have a positive slope of the tangent line for a long period of time. Positive slope of the tangent line means it's going up. If it's going to go up for a long period of time, it seems like I might be smart to start my graph down low just for my own convenience so I don't run off the top of the board. So I'm going to choose this. I'm just going to, let's erase these 2 here. I'm going to say it starts out down here, and initially, it just, for a tiny bit, it starts going horizontal. Now it might start curving up, or it might start curving down, or it might go flat. We'll see about that in a second. Any questions about that discussion, that there's the ambiguity about where to start? There's no correct answer there, but you might choose it for your own convenience just by looking at the fact that the slope of the tangent line is going to be positive for a lot, means I'm going to be going up a lot of the time. Okay,
Hey,
how do I decide which way to trend? Do I start curving upward? Do I start curving downward initially, just as we move a little bit more to the right? Or do I sort of stay flat there? Who's got an opinion about that? Jeremy?
So because the Vx graph is negative, the slope of the xt graph is going to be negative.
That's right. So here, the height was 0 and the height is becoming a little more negative. That means the slope of the tangent line starts out 0, but it's got to become a little bit more negative. And becoming more negative as time goes on means turning over. So the slope of the tangent line is negative, not positive, but negative. So that's like you're at the top of a parabola and it starts going down like that. That's just for the initial bit, right? We've still got some more complications to go with there. So it would definitely be wrong to have this keep going flat or trend up like that. It's definitely not doing that.
okay, but could it, like in the last problem we just did, it was a parabola and it was like looked like it was going up, but like wasn't, just barely curving. So like, you know what I'm saying? Because the slope of the last problem we just did was also negative for the velocity. So could you draw it like the top left corner one?
You mean could it just go straight down like that?
Yeah, like the one on the X above that, it's like a parabola, but it's like curved. It's still going up, but it's like at a downward velocity. So could you do that also for this one?
Let me just draw a picture and see if you'll agree with it. Now I'm going to draw it in a different location because we already decided it didn't really matter. Are you suggesting that it might go like that?
Yeah.
So can anybody derive a contradiction between this little bit of a curve up here and what's shown down here in the velocity? Yes.
The curve that you drew in blue is positive.
Well, its value is positive. Is that what you mean?
The slope is positive.
The slope of the tangent line at t equals 0 looks like it's very positive. What's the height of this curve down here?
Okay. Yeah. Okay. I understand.
Right.
Because
So
below
that
X,
means it's got to be
0.
coming out horizontal.
Gotcha.
It can't be automatically going up or automatically going down. Just for that slightest first bit, it's coming out completely horizontal.
I understand because it's
Good,
below
good,
the
good
t,
question.
that t value 0.
Okay, so that trend continues. The slope starts to become a little bit negative, and I'm going to sort of temper my enthusiasm because I don't have too much room to go downward. So I'm trying not to curve it too far. But it does keep getting a more and more negative slope of the tangent line because the height of this curve gets more and more negative until we pass this line here. So it starts becoming a little negative, more and more negative slope of the tangent line. So it looks like a piece of a parabola curving down. Yes.
I think there's
I think your computer might have.
No, it's the display. You guys, can you still see the Zoom stuff? Are you guys with me? Can you hear me?
Yeah, we can see stuff fine.
Okay, and you can see the board.
Yeah.
Somehow our display.
Yeah.
The board's all we can see.
I see. For some reason, the little control thing just powered off. So
Well, the board is all we can see right now.
maybe it
Yeah, we
thinks
can see the board
nobody's
fine,
in
but
the
nothing
room or
else.
something. Okay. It looks like it's coming back on and powering up. Okay. All right, so there was that first trend. Oh, I didn't do a very good job of keeping this line straight here today. All hand drawn. I got to stand right in front of it and say, there it is going straight down. So it should continue that trend until it hits that time. And then what? It was going down on kind of what looked like a parabola, but what happened? How's it going to change as I move a little bit past this blue dashed line there?
curving upwards.
Yeah, so curving upwards. In other words, where's my green? Here it is. It's not going to have, this curve isn't going to have a positive slope. What you're saying is this one up here starts becoming less and less negative until this time, right? And that means the slope of the tangent line stays negative, but it becomes less and less negative, and that means it curves like that. And at this point, the height is 0, and that means the slope of the tangent line should be 0. So I should be coming down and reaching the bottom of a valley. I know that's a little bit subtle in the drawing, but I'm trying to leave myself room to go up because of what we saw coming in the future there. Okay, same trend continuing. Height is 0 and then becomes more and more and more positive until this time. That means the slope of the tangent line is 0 at this time and becomes more and more and more positive until we reach this, oops, wrong color, till we reach this particular time, something like that. And at that point, it's got a pretty large and positive slope of the tangent line, which corresponds to a large and positive height of the curve down below. We're just reasoning in reverse and imagining if the one above had a certain shape, how would that affect it down below? And sometimes we can see a contradiction. All right, how to continue this on into the last region where this one, you know, I don't know that I'd call that flatlining, but it definitely becomes horizontal there. What should this curve do?
Straighten out, but
Pink.
not flat.
Straight, but not flat. Okay, suppose I said, okay, there you go.
But the slope needs to be greater than what it previously was because it's a higher value.
Yeah, you know, so a lot of times this is sort of qualitatively correct over here and qualitatively correct over here, right? Positive slope of the tangent line means positive height down here, so everything looks okay. Until you look at what happens right here in this kink and you say, look, the slope of the tangent line was really big right before this time, and then it jumped down to something less positive at that time. That means the height of this curve should be really big and it should jump down to a lower value after that if there's a kink that I've drawn in my curve. So the kink is the problem here. It doesn't jump down to a lower value instantaneously and stay there. Rather, whatever height it was at right before that time, it maintains that height. And that means whatever the slope of the tangent line was right before this time, and it looks like it's sort of going up in that direction, it should just keep going off along a straight line. It's hard for me to hand draw it like that, but I'm trying to draw it with no kink in there. It's like you've connected a line segment to a parabola without making a kink in it. Still, to me, looks like there's a little wiggle in there, but I can only do so well hand drawing. Okay, so that's an example of how to do this process. Why don't you guys, so any more questions on this graph? Other ways you might have drawn it? Good. Why don't you guys try to do this one down here again, just for practice, and then we're going to do one more practice one of this variety. I'm going to start drawing the Vx versus T curve for this one, and we're going to do the same practice process. If you're quick with this last one down here, you can start on the next one. Okay, I'll draw this curve in just a second. It's not super challenging compared to what we were doing. But if you're done with that, try to go up and down on this one. Draw the X and the AX versus T curves. Anybody have any questions in here?
So this whole section right here is positive, would that just be like straight line up here?
Yes, for that curve.
Right. And then that's up to the zero.
Right.
That's zero.
That one's pretty easy. It's just a couple of flat lines.
This one is like the one at the top, the last one. Whenever it gets to the top, like I know it increases, but like, does it level off or just like immediately? Because the slope would gradually increase, right?
Yeah, so first of all, the height is positive. So that means the slope of the tangent line is positive. We're talking about something doing this. And until we get, well, in fact, if you look at the whole Vx versus T graph, it never goes negative. So we should never see the graph we're going to draw going down like this, ever. So that's a contradiction with the other side of your volcano. So think about how you got it.
Like
The most you can do is flatten
And then it
off.
would go like that, flatten off.
Yeah,
Yeah.
yeah. How's it going?
Okay, I'm still trying to figure out how to do that.
Yeah, so here, again, we're looking at slope of the tangent line here, and you see the slope of the tangent line would be negative for that first region, because negative slopes are like that, positive slopes are like that. So, and the slope of the tangent line is constant and negative, right? No matter whether I catch it there, or there, the slope of the tangent line is the same. So that corresponds to the height of the curve down here. So it's staying constant and negative, flat in the negative region.
So it would be constant for each one of those?
Yes, so you're talking about three constant graphs that where it just jumps to another constant level. Mhm. You guys still working on the third one over here? Yeah, I'm going to give you about one more minute and then we'll come together and do them piece by piece together. Okay, let's finish up the middle column here. I'm trying to go from slopes of tangent lines here to heights down there. Slope of the tangent line is at first constant and negative, and that means for that first region, the height is constant and negative. Then suddenly, the slope of the tangent lines are constant and positive, and that means until this time, the height of this curve better be constant and positive. It looks like the slope here is a little bit more positive than this one is negative. It's a bit of a bigger angle, so I tried to make it a little bit higher. But, you know, we're just trying more or less for qualitative agreement. And then finally, for the rest of it, the slope of the tangent line is 0 all the way across there, and that means the height of this curve should be 0 from there on out. Questions on that AX versus T? Not too many tricks there. It's this one that might cause a little problem. Okay, so again, where should I start? Positive, negative, or 0 for the very first point on there? What do you think?
It doesn't matter, but
Doesn't matter. Now, what would the intelligent choice be? Positive, negative, or 0?
negative.
Probably negative, because look, the height of this curve is everywhere positive. The lowest it gets is 0. It's got a lot of positive in it. That means the slope of the tangent line is at worst going to be 0. When it's positive, it's like this. And that means it's never going down. Nowhere should the graph we're going to draw up here should never be heading down at any point. The worst it can do is flatten out, but most of the time it's going up in various ways. And that means if I don't want to run out of room, I better start out low. I've got that freedom to choose where I start, so I'm going to choose to start down here. I still may have to temper my enthusiasm so I don't shoot off the top of the board. We'll see how that goes. Okay. Now, given that I've chosen the starting point, how should I begin going to the right there? Should I immediately go up like I'm on a line that's going up, or immediately go down, or come out flat and maybe I can curve up or curve down later? I'm sort of purposely ignoring Jeremy only because he's answered so many times.
You repeat the question.
The question is, now that I've decided, I could start anywhere on here, but I want to know, should I immediately start going up or immediately start going down, like I'm following a line going down or following a line going up, or maybe just immediately go out straight, like maybe I'm on a parabola at the lowest point and I'm going to later start curving up, but should I start out going horizontal? You're right, I can't go down because that would correspond to a negative slope. If I chose this one, that would be a negative slope of the tangent line. This height of this curve would have to be down here in the negative region. All right, that's good. I still have the ambiguity of the 0 or the positive.
Horizontal.
So I think someone on Zoom said horizontal. If we
Yeah.
cut horizontal, and then maybe later on I can start curving up, but just for a moment I'm coming out horizontal. Let's try out that hypothesis. So forget about this one. If we were horizontal there, the slope of the tangent line right at t equals 0 would be 0. And that means the height of this curve would have to be 0. But it's not. So there's a contradiction there, right? This cannot be correct because then this curve down here would have to start at 0. Slope of the tangent line being 0 means the height of this curve is 0. Slope of the tangent, going backwards from there, the height of this curve is clearly positive at t equals 0. And that means right at t equals 0, this curve has to already have a positive slope of the tangent line. Now, I've got to temper my enthusiasm, so I'm going to make it positive, but maybe not quite so positive because I got a lot of going up to do here. Any questions about that? Why I didn't choose horizontal there? Just doing the barest bit of the curve as we're heading over. It's got to immediately have a positive slope of the tangent line right at t equals 0 to have a positive height at t equals 0. All right. As we move to the right, the height gets bigger and bigger and bigger for a while till we reach this time. That means the slope of the tangent line has to get bigger and bigger and bigger for a while. Oh, I'm getting a little bit worried about how fast my graph is going up, but we can do that. It's like that we're on part of a parabola and it curves up a little bit like that. So it's on a curving piece. I'm trying not to curve it too much so I don't shoot off the top of the board. So the slope of the tangent line is positive, but it's getting more positive. Height of the curve is positive, but it's getting more positive. This is the most positive height this curve attains. That means this is the most positive slope of the tangent line it should get to. After that point, the height starts becoming less and less and less positive, and it goes down to 0 by here. So that means the slope of the tangent line should become less and less and less positive and reach 0 by the time we're at this line. So that means we're already going up, but we got to sort of reach a slope of the tangent line of 0. It's supposed to look like a smooth curve. I'm doing it by hand, so it's not so compelling there, but it's like it's coming to the top of a mountain. The height was almost 0, but still positive and went to 0. Slope of the tangent line was almost 0, but still positive, and then went to 0. And then after that point, slope of the tangent line is, height of this curve is 0. That means the slope of this tangent line stays at 0 until this time. Slope of the tangent line being 0 means we're on a completely flat curve. Again, this doesn't look quite right to me. This is supposed to be, curving up smoothly to there. And then for the last bit, all of a sudden, the height of this curve goes from 0 to something somewhat positive. That means all of a sudden, the slope of the tangent line turns from 0 into something positive, and it stays constant at that positive value. So, maybe goes up like that. Again, we can quibble about some of the little details on this, but I think we've gotten most of the qualitative features correct, and that's what I'm concerned with in these drawing exercises. You don't want to look at this and say there's an obvious contradiction between these two graphs. And always, a lot of times it helps to just go back and forth and check little details, both upwards and downwards. Okay, let's finish up with the AX versus T curve. There's nothing especially hard about this one. Slope of the tangent line until we reach this time. Slope of the tangent line is constant and positive. Height is constant and positive. After that, slope of the tangent line is constant and negative. That means the height of this curve is constant and negative until we reach this time. Slope of the tangent line is 0. So the height of this curve is 0 until we reach this time. Slope of the tangent line is 0 again. So the height of this curve stays at 0. And you might say, well, nothing can really change its velocity instantaneously. So maybe if you took out a microscope, you would find that this curve actually goes up at a very rapid rate between those two heights. And that would mean there was a period where the slope of the tangent line was really positive, and maybe there's a little microscopic blip in there if you really wanted to be realistic. But let's not get into such realism when we're drawing these graphs, unless there's a good reason to believe it. Any questions?
Dr. Kelly, I have a question.
Yes.
If you wanted to go from the acceleration graph to the velocity graph, how would you distinguish between the two 0 slopes?
So you're saying
From the acceleration to the one right above it,
yes.
there's the two 0 slopes, but then one of them is at 0, one of them is at positive on the velocity. How would you tell the difference between the two?
Yes, so you couldn't really tell the difference between the two in the sense that if I started with this, we already had the discussion of, if someone gives me this graph, there's an ambiguity about where to start this. Now, all the rest of the graph is determined, but I could move the whole thing up and down, and I wouldn't change the slope of the tangent line anywhere. And this graph would look exactly the same. So there's lots of graphs I could form up here, which are consistent with this one. The same thing is true for going from here up to there, right? If I took this same graph, forgetting about the one up there, if I took this same graph and moved the whole thing rigidly up or down, it wouldn't change what this one looked like at all because the slopes of the tangent lines would be the same everywhere. Now, if I move this graph up, let me just draw a different version of it up here. Suppose that we started with this and I said I wanted to get to the position versus time. And I had chosen something different in going up here. So my graph instead looked like this, what I'm showing in green there, just translated upward from there. All the slopes are the same here, and therefore this graph would look exactly the same. But notice now, rather than having a 0 height, this has a constant positive height. And that means that this graph would actually be substantially different there. Constant positive height down here means constant positive slope of the tangent line up there. So when you start going up like that and changing something down below, it can have drastic effects up above. I'm not sure if I'm getting at your question, but that's what I thought you might be asking about.
Mostly, yeah.
Yeah, so it's a little bit complicated. You know, if I change my acceleration, it's kind of like this. If I say I'm going to have the same acceleration, but I'm going to change what my starting velocity was, right? So maybe I'm accelerating I have a positive x acceleration, but I have a negative x velocity at time t equals 0. Well, what's going to happen if that stays constant? I would slow down in the negative x direction and then start speeding up in the positive x direction. And maybe I wouldn't have gone anywhere by the time I get to a later time because I went backwards for a while and then went forwards. But if I have that same constant positive acceleration, but I start out with a 0 initial velocity, I'm going to start accelerating in the positive direction and just go way far away. So the motion can look quite different in those cases. So it's really hard to compare, you know, what happens as you go up like this because it seems like, well, going from here to here, there's this trivial ambiguity. I'm just moving the graph up and down, but it's not trivial. Look, this person was at rest and this person was moving, and that seems like a big difference to us. Going from here to here, it doesn't seem that different, right? I mean, I would say if I move this graph up and down, that's just a matter of where I started on the x-axis. It's a small change. But if you change my velocity from positive to 0 or negative, that's a huge change. So it seems rather substantial. Feel free to sharpen your question if you want to. Anything else before we break for the day? Yes?
So when you're doing the VX graph, and you're doing that one first before you do the top one,
This is taking forever.
negative, if it looks negative, that doesn't necessarily mean the top one is negative, it just means it's not as positive.
Are you talking about the value of this curve or the slope of the tangent line?
The slope of the tangent line.
Yeah, so here the slope of the tangent line is negative. You're saying that doesn't necessarily mean that the value of this curve is negative.
Yeah.
Yes, that's true. The reverse would be true. If the slope of the tangent line of this curve was were negative, the value of this curve would be negative. The height of it would be negative. But that is not true going upwards. I don't know where this curve should be, even though I know what the slope of the tangent line is down here, or even though I know what the value is up here. There's some ambiguity, but it's all well determined going down. Anything else? Okay, I think we've gotten through a good discussion of the basic definitions of Vx and Ax. And now we're going to get into how to solve problems of motion. In other words, if we're going to assume in the reading that you'll do for today, which is for tomorrow's meeting, if the acceleration is constant, which we'll find happens a lot. If all the forces acting on something, we'll find out later on, are constant, and the acceleration will be constant. So it's an important special case. What does the motion look like? So that's what's coming up in the reading. So feel free to leave. I'm going to leave Zoom on just in case some people want to stay to ask additional questions. But if not, I'll see you tomorrow. For those of you who are coming in, we're meeting again in Young 101, our original room. Same meeting time as today, 12:55. Same time period. Thank you.
Dr. Kelly.
Yeah.
So I know we just kind of got like access to like the homework. Do you think like we would have enough knowledge to like start it now or like and like finish it now, or should we like wait until tomorrow after class? Because I know it's due like September
I
1st.
think you would for, I don't know exactly the problem numbers, but they tend to go in the order in which I'm doing the sections. So if you look at the ones toward the beginning of the assignment, they probably have to do with the ideas of velocity and acceleration. But without looking at the assignment, I don't know where that transition happens, where you need the last set of sections, which you're going to read today and read the video and watch the videos about when that transition happens in there. But there might be a possibility to do some of them. Certainly by the end of day tomorrow, I'm hoping we're all through it. And so you have the weekend to work on it and Monday to ask questions.
All right.
So it's worth a look, I think, Andre. What's up, Jose?
Is there any more practice on these type of things or the graphs?
Not on the homework. There might be, I tried to find the ones that I could find that were closest to it. And even in our textbook, there's not a lot of practice with it. We will do some more practice in Tuesday's lab.
Okay.
And probably before the first exam, I'll hand out a random grab bag of practice problems, some from old exams and whatnot. And they will have one or two of these kinds of problems to practice with too.
So I'm assuming this wouldn't be like a major part of our exam.
It's not going to be a major part, but I will say it's almost certain to appear on there. It's not going to be more than one problem's worth out of the exam.
All right.
Yeah.
Thank you.
All right. See you tomorrow.
See you tomorrow.
Anyone else? Yeah. Go ahead.
Yes,
Sorry.
Dr. Kelly. One thing that I was noticing I was getting tripped up on was translating from the velocity graph to the position graph. So when we're looking, so say the one on the far right on the board, when we're looking at the first part of the graph that's of the velocity graph with the upward slope, whenever we see that, we can think and interpret it as kind of the first part of an upward facing parabola. When we kind of see that when we're thinking of back translating it. Does that make sense?
Yes, I mean, speaking personally, I would say that I don't immediately see that. The way I say it to myself is the height is positive and getting more positive. And that means the slope of the tangent line is already positive and getting more and more positive as time goes on. Oh, that looks like a parabola to me, but I don't immediately see it and look at it and say parabola. It's very mechanical the way that I think about it. And so you just got to get used to piece by piece going up and down and saying, I know the relationship. Slopes of tangent lines go to heights. That's why I go down below. Or if I know a height below, that's the slope of a tangent line down below. If the slope of the tangent line is positive and getting bigger, that sounds kind of like a parabola. I don't know that it's exactly a parabola. That's the kind of shape qualitatively speaking.
Okay. Thank you.
You're welcome. These kinds of problems, it's very easy for you to make up your own practice problems, and you can try to do them, and we can talk about them in office hours, if you want more practice with this. I was just telling Jose that, we're going to do more practice with it in Tuesday's lab, and also before the first exam, which I think is a week from Monday, yikes, I will give out some random grab bag of stuff that's just kinds of problems that may be from old exams or just old practice collections. And some of them will have to do with graphical stuff too, so there'll be more practice on there. But you can make up your own practice if you want.
Okay, great, thanks.
Sure.
I had a question concerning like the acceleration to velocity graph of the last one. So say you were given the acceleration graph, but you know how in the velocity graph there's like a break, although the acceleration just stays zero constantly. So say that you didn't know that there was a break, would it be acceptable just to like create a velocity graph where it just stayed zero the entire time afterwards?
Yes, yes.
Okay.
I mean, because as I mentioned earlier, in order to really specify this break right here, it's sort of like, there's got to be something that goes up at a very steep slope. And so in order for me to indicate that there's a break, I have to have a region where the height of this curve very quickly goes up to a positive value and back up down to 0. Positive value would mean very positive slope up here. If there's nothing like that indicated, the only reasonable thing to do up here would just be, of course, nothing's happening down there. You just stay on that same flat line.
Okay.
That's a good question.
Okay. Thank you.
You're welcome.
Thanks,
Anyone
Dr.
else
Kelly.
on
See you
Zoom
tomorrow.
hanging out to ask questions? Looks like not.